many isotopes do we have? How many isotopes do we have? 12. What's an isotope?
Oh yeah.
12.
But we need like an
Isotope. Do you remember what an isotope is? Does anyone remember what an isotope is? Maybe we should have done this. Really quick, everyone pause for a second because I think everyone. Can everyone look up front for a sec? Guys, who remembers what an isotope is? This would have been something really good to do before we started the lab. Who remembers the definition of an isotope? Anybody? Do you remember?
I'm sorry. It has the same element but has a different number of neutrons.
So, if we're pretending that our pennies are an element, all of pennies all together, every single penny in the world is all the same element. How many isotopes do we have in our standard?
So, isn't it atomic mass?
Let's talk about these. You counted these. So we have, how many different types of pennies do we have in here? Two. Okay, what makes them different? Some are before 1982, some are after, but what's the main difference between the two? How much they weigh. So, if an isotope has a different number of neutrons, which means it has a different mass, how many isotopes do we have? And what are two different types of isotopes? One's from... Yeah. So before 1982, yeah, let's pause and answer your question first.
All right. So hydrogen bonding between the hydrogen atom and oxygen, nitrogen, and chlorine, because they're the electronegative ones, right? And water is made up of oxygen and hydrogen.
Okay.
So isn't that an intramolecular? Because it's within this
Here's
water
the difference.
molecule.
Here's the difference. So wait, can I have, so here's our difference. Can someone come up here and be two hydrogens for me? Will you guys be hydrogens for me? I'll be an oxygen. Okay, so let's imagine that these are our pairs of electrons, because this is the first thing I grabbed, okay? And you guys have, so we're sharing our pairs of electrons, so hold on to it. And now we're a water molecule, right? So we're sharing these electrons, we're holding on to them together, okay? So we're sharing them, that's a covalent bond. So now, can someone else come up here? 3 people, I need 3 more people. Whoever's in the center is my oxygen. Okay, hold on to it, here's over here. So, our oxygen is greedier for those electrons, so I'm gonna hold them closer to me. So you hold them closer too. This makes me more negative. So what's gonna happen is we're gonna get attractions between Aaron, who's now positive, and me, who is negative. So okay? So because I'm a little bit negative and Aaron's a little bit positive, we have a polar attraction to each other. You guys can see this? It's hard to see from up here. So that was our H bond. That's when we hooked arms. So there is, you guys can see that. We do have these bonds between oxygen and hydrogen and another bond between oxygen and hydrogen.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium.
These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom.
When my body gets hot and it sweats, that heat excites some of the water molecules on my skin to the point where they break those hydrogen bonds and they evaporate away. And when they escape, they take that heat energy with them, leaving me cooler.
Instead, it might bond to the nucleus itself, and then the nucleus would become very unstable. It might then split, and as it did so, it could release some of its vast store of energy.
The temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
The sun is a mass of incandescent gas. sun is hot, the sun is not a place where we could live. But here on earth there'd be no life without the light it gives. We need its light, we need its heat, the sunlight that we see. The sunlight comes from our own sun's atomic energy. The sun is a mass of incandescent gas, a gigantic nuclear furnace.
Recording. Why do you think we're heating it a second time?
To make sure it's actually like heated, like all the water's gone since we took it, but then cooled it.
Yeah. So how are you gonna know after you masked it again whether you lost all the water or not, or if you lost more water or not? Well, it wouldn't go up. You're not gonna gain anything.
I mean go down.
So if it goes down, what does that mean?
It means that
There was still water.
There was still water. But scientists can use this, chemists use this in their research. So this is actually something that I had to do in my research, where if you make an unknown compound, a lot of chemists make unknown compounds, and then after they make them, they have to figure out what they are. And one of the tests they use is they send it out to another chemist, and they can send you back the percent composition of your compound. They can tell you exactly how much of it is carbon, how much of it is hydrogen, how much of it is nitrogen. And from that, you can figure out what your compound is. And so we'll do some problems like that later. When you guys get back to your desks, you can start working on your calculations, and I'll come around and see how you're doing. Throw out your gum when you're done. Please throw out your gum when you're done.
So you just add.
Yeah, you just add it up, and then whatever you have. So it's kind of like distributing. So if you want to figure out the total mass of nitrogen, how many nitrogens do you have? You have one inside, but how many total do you have? Three, right. So how many hydrogens do you have total? 12. So when you're doing these percent composition reactions or calculations, you have to use that total number. So make sure you distribute your thing.
All right, thanks.
I think I'm doing this right. I can't tell anymore after that.
Mine would be. You went from 2.9 to 2.8. Wait, so the 2 is sugar, right?
How are you guys doing?
Velen do look like stronger because you know for the hydrogen. Oh yeah. And Velen look like it's like connected like so it would be great. I don't have backup. Why would hydrogen be stronger? I don't know because we did that thing.
Okay, everyone discuss it. Let's take a vote. Who thinks hydrogen bonds are stronger? Raise your hand really high. What is the point of writing a formal lab report? Why do chemists and other scientists write formal lab reports? What do you guys think? So scientists can repeat your process. That's good. Gabe?
Also, so you can prove your process.
To prove your process. Okay, prove what you did was right. Okay, anyone else? Have any ideas? So they don't make the same mistakes again. That's good. That's good. These are all good things. Yeah?
And usually, like, you do it because you have like an idea of like ready creation. You don't want somebody else writing it, so you write it.
Copyright. You have copyrights on your stuff. You invented a new molecule that cures cancer. You're not going to want some other guy publishing before you. Okay. If you decide to go into chemistry, the further along into your chemistry studies, the more narrow your field gets. You're going to end up picking a field, and there's only going to be so many other chemists in the world who study the same thing as you. So you want to share as much information with each other as possible. Today, I wanted to give you guys a lab where we had a little bit simpler calculations that was a little bit fun. But I also want you guys to see the setup of a formal lab, because in a lab or two, I think maybe a week or two, you guys are going to be writing your own formal lab report. So I wanted to give you guys a quick little idea of what the different parts of a formal lab are. And when we get to our lab where we're going to really write it out ourselves, I'll give you a really nice, detailed rubric of everything you could ever need. But for today, we're just going to do a simple one, okay? So, we already went over our purpose, our materials, and procedure. Your results section is where you take all of your data, all of your calculations, and you put it nice and beautifully into one little space for me, or for whoever's going to read your lab. So I gave you guys a data table for today. In the future, you're going to have to make your own data tables. You have to think about the best way to put your data out there. And then also, when you do your results section, you need to show me your calculations out in full. If you have to do the same calculations like 20 times, you just have to show me one sample equation. Okay? For this conclusion, I want you guys to just kind of give this a shot today. The first part of our conclusions is a summary of the lab. You say what you did, what the point was, and what you got as your results. Summarize the lab and the results. The second part of the lab is going to be answering these couple conclusion questions. So they're similar to the questions we've been doing in other labs where they're bulleted. But instead, I want you guys to write this out in paragraph form. Full sentences, paragraph form. Talk about what the point of the lab was, what your results were, and then answer your conclusion questions. Okay? Sound good? I think we're just about out of time. Yep. Wow. Boy, that would be perfect. Okay, so
we measure it with it, and then we measure just the evaporate, and then we subtract for the higher level. Measure the mass. No one cleaned the scale. That's destroying. You put the gum on the scale, and then feed it. We always put it on, and then take it away from the gum, and then measure the evaporate, and then subtract the evaporate from the thing. That will just give us more chances of having mistakes. It's okay. It's not like we're not. You don't want to eat it. We can give it to Denise. Okay.